us in trying to see in a simple model chaos can arise, in a model which we can pretend to kind of solve exactly, and then we'll see what are the difficulties. All right. So the model, you remember, was chaotic. You remember the problem, right? I mean, the experiment that we saw was that there were these buckets or, leaky cups on a ring, and there's a inflow of water, and then the motion starts becoming chaotic. So the way we wanted to set up this problem, so let's say that the radius of my handwriting is terrible, the radius of this wheel is, right? And we are going to have on any line segment, on any segment, on any arc of that wheel, we are going to typically have the mass distribution, which will be essentially a function of both the angle and time, right? Because the amount of water which is contained on that ring is going to be time dependent. And because things are leaking at different rates, it's also going to be angle dependent, all right? For convenience, and I might mess this up as we go along, but I'll assume I won't. So for convenience, we will see that the angle, this 12 o'clock is theta equal to 0. And let's say this motion, it doesn't really matter. I could easily well choose the other one. This is at any given point of time, it is rotating with a rate omega t. Okay, what else do we need? What we need is, what is the net flow of water which is being pumped in? So that will be like a forcing in the system, if you like. That will, of course, depend on where you are in this angle. And we call that okay. What else? What else? What else? Of course, the cups are leaking. So we are going to put some leakage rate. Right? And because we are eventually, well, not really, but we'll make some contact with Navier-Stokes, which you saw had all these dissipative, etc. terms, there's also going to be some damping rate. Now, where can this damping rate come from? This damping rate can come purely from mechanical reasons, right? I mean, you have a sort of Ferris wheel which you're rotating, you've put in whatever oil or grease you could to make it as frictionless as possible, but it's never truly frictionless. But there's actually another more interesting physical principle behind this, and you guys can go ahead and think about it, is that when you are putting in water, right? So you're adding, and then this starts moving. So there's a net angular momentum, which is allowing it to move. So there's a spin up happening in the wheel. Now, what can possibly oppose that spin up? Okay, that's so, but from the point of view of the algebra, essentially, I'm going to try and reduce it to a convection-like problem. Not really. I'm going to try and reduce it to a model of a model for convection. I will use the standard notation. I will say nu, some damping that's going on. All right, do I have everything? Is there anything else I might need? If I need, I still have some space. I can continue adding it as I set up conservation laws and I see that I actually need more symbols or more things. Well, I do need something, but that's related. The total mass will be related to the mass density if I'm going to integrate everything out. And in steady state, one would assume that to be a constant. Right, the mass will be essentially the mass of the water. I mean, you can have a constant background mass of that ring, which would be realistic, but you really don't care about that mass. All right. So what we are going to do is the following. So on this board, let us imagine that's where the Ferris wheel is. Let's try to derive it together. I mean, there'll be some steps in the algebra which you can figure out yourself. And at any point in time, so that's the full wheel. I'm going to focus on the small arc. And let's say this arc. Okay. Let's pretend this to be an arc, and both the straight lines I've drawn to be equal and of size r. Let's say this is some angle theta. This is some angle theta. In the global thing, remember, this is 12 o'clock, 0 degree. So I've taken an arc here. And so it subtends the two angles, theta 1 and theta 2. So question is, in time delta t, so I'm assuming delta t to be small, so I can assume omega. We saw that omega varies a lot. But actually, this is a good game. I mean, y'all can set this up. It's trivial to set up. And then, try and have fun with friends trying to predict which way the thing will turn in the next 1 minute or the next 10 minutes, etc. before you. Please don't do it near our offices. It will become wet and all of us will slip and fall. Okay. So the point is, what we are trying to, what we are doing is the standard game we play in physics, that dt will be small. So I will hold omega to be constant. And in dt, if this is sort of moving in this direction, yeah, that's the direction I chose. Then what you will have, so you're looking at this from outside the wheel. So essentially, this little bit of material will go out of your field of vision, right? And this little material will come in. All right? Everyone with me? And what is this? These two little pieces? These two little pieces are nothing but omega delta t. Right? Because you're turning at omega. In delta t, think about a steering wheel, or if I had a wheel, it would be simpler, which I don't. So essentially, this is the cross section of the wheel. In delta t, I turn like this with omega, which I've assumed to be constant over that time window. That's what I have. All right. So now all that remains is to try and figure out how much mass of water or stuff that was in this ring, what was the change in the mass? So physically, what can change? Why could there be a change? One is because you're injecting things at the rate q. So you get some stuff in because of q. You are leaking out stuff at the rate of k, right? So in terms of unit mass, that would be km. Plus, there is this additional contribution, which is coming from stuff which was here. You remember I had the mass density, stuff that was here. So things which were here, things that were here. How much mass has changed here because this has moved. So could you all try to think about the change in mass? So what we are after is, what is the change in mass? Let's call the total mass in this segment, the change in mass as delta m, equal to what? You have all the contributions from the different terms coming in. How do you actually set up the equation? Oh, you have to monitor this. But you have some other stuff to do for tomorrow. You can turn it around and I can keep an eye on it. Sure? Sure. So essentially, what was the first thing we said? The first thing we said was how much stuff is going in. That's going to be positive contributions. All right. And the leakage, I guess I tried to write kappa, but I'll stick to K. Right? And this has happened over time delta t. I'm just writing it big so the people online can read. Okay. And then there is a change of mass just because you've rotated, right? It's not necessary that at θ1 and θ2 you had the same amount of water, right? So then you'll have right. Okay. So now if this is a small arc, that's the typical approximation we make, right? θ1 and θ2 is small, then you immediately see that you can write this difference of the masses at θ1, because this is common, you can take omega delta t out of this. This will just be the gradient, the del m del theta multiplied by d theta, right? You guys have it, I mean, this sort of, limits and delta, some going to zero, some not going to zero, you guys are sort of familiar with, right? I mean, okay. If not, let me know. And so what we'll have is delta t so m θ1, m θ2 with that sign convention, this will be that's not dimensionally consistent, of course. There's an omega sitting here, right? Thank you. Very good. And now we divide everything out by delta t, and I'm not going to sort of abuse your intelligence, and then we can write this as this is what one of you was desperately shouting from the back, right? D theta, d theta. All right. Very good. So now we have what would be an integral differential equation, because we have a derivative on the left side, we have an integral on the right side. But now we can make use of a certain trick and convert and get rid of the integral. So what's the simplest trick that you can think of? See, the point is I have a derivative here, I have an integral here. If I can write this as an integral in theta, then life is simpler, right? So what is it that you can do? I mean, we already have a clue there. We can write this m in terms of m d theta, right? I mean, that's what it is. Right, and any given point of time, the total mass there was the mass density, which I integrate over theta. I can interchange the action of the derivative and the integral here, and then eventually the final equation that I want to get at okay. So probably I can, all of you will be rather quiet and nice if I say, okay, that solves the problem and walk out of the room, right? But it really doesn't, right? I mean, it's given me an equation which comes from the conservation of mass, which tells me about how the mass density is going to evolve as a function of theta and time. Again, don't push the analogy at all, but in a sense, this linear equation is a bit like what it's a partial differential equation. So it's a bit like the Navier-Stokes, which tells me about what happens to u as a function of x and t, and there you have derivatives, spatial and temporal. But this is what it is. Okay. However, there is another principle that we can use. That's conservation of mass. We would like another set of equations to actually describe the full dynamics. And once we have that, then you'll see something sort of rather beautiful follows from this analysis. So what is it that you think we can apply now? What's the other sort of very basic classical mechanics? Right. So the question that you're asked in every sort of interview, right? Here, of course, Newton's law. Is that for me? There's a, okay. So here, of course, what we do is we apply Newton's laws of motion, as Jitendra was sort of trying to nip it. What we'll do is apply the conservation of torque. Huh? So what we'll write down is the effective equation for the torque. So I'll just keep that there because I'll need it. I'll erase maybe this. This part I can erase for you guys. Yeah. It's not too complicated. I could do it with a few mistakes. You guys can do it even better. All right. So what are the different forces acting on this? One, you have a clue, right? Because I had two terms that I haven't quite used here, right? I have the nu and the r. So I need to somehow put that all in, huh? Otherwise, what's the point of writing them on the blackboard? Okay. So what we'll do is we will now try and apply Newton's laws to get this, to close this set of equations. Okay, so essentially, all of you have seen moment of inertia, omega, etc. So all of you know the basic equations, right? So this is, of course, a damping term. So let's go with the simplest approach that we can, and we'll just call it minus nu omega. That's a bit like your standard friction. Plus, what other external forces can apply in this problem? Gravity, right? So plus you have the gravitational torque. And that gravity, so essentially, you see, I'm trying to convert this problem into a problem of a pendulum, which is something that most of us know how to handle. So plus gravitational torque. Okay, so all of you are good at working out the gravitational torque for this model. So again, you have this line segment, you have the different angles. Gravity is acting downwards. What would the gravitational torque be? Again, take an infinitesimal section dm here. So you'll have gr sine thetas, etc., coming in, right? D theta. I mean, depends on your sign convention. So you could have a sine or cos it. And then exactly do all of that. So what do you get at the end of the day? You guys will work it out. Just to let you on a secret, in the morning when I was doing this derivation, that's when Ritik came to my office, I got this term wrong because I had calculated something incorrectly and the final results were wrong. So I had to go back and, so anyway, you can play the game and you'll figure out that the gravitational torque will come to this. I mean, it's not surprising. There's G's and R's and you have the right combinations of sines and cosines. Very good. Still doesn't entirely help us, right? So now we end up having essentially these two sets of equation. They're coupled. So let's have a quick look at these guys. That's not zero. Let's have a quick look at these guys. So what these coupled equations tell me is the following. Suppose someone, I give you the initial conditions. I say that mass is distributed on the ring, let's say, in some way. Then I'm able to solve that equation here. And I can solve, in principle, of course. I solve this equation, I get m as a function of theta. I plug it in here and get the omega out of this game, right? And so in principle, I can solve this coupled set of partial differential equations to actually predict omega versus t and solve it, let's say, numerically, because I don't see how one can solve it on a piece of pen and paper. But there's a trick that we will use. And that trick will help us to actually reduce this problem to something which is what you saw in that video. Right? And that trick is quite useful. That trick you will use in other places in fluid mech when you have a less fascinating course on fluids, once you do your semester in college. But before that, I just wanted to point out one thing, and this I think is an important point, is the following. I should have mentioned it when I drew that omega t going in that direction. You see, I could equally have chosen my direction of motion, for the instantaneous case, which is when it's turning in this way. There's nothing really to prevent me from doing it, right? So what happens in a real system? Suppose and think about it. I'm not going to give you an explicit answer right now. Suppose you guys go back and, the easiest way to actually do this experiment is for those of you who are on campuses and have bicycles. Get your friend's bicycle, take off their tire and use it, right? And sort of puncture some holes and make it. So now you can do this experiment 3 or 4 times with the same tube. And each time you'd probably, you're very likely to see that the wheel starts spinning in a different way. Suppose you do this experiment 100 times. You do it once, you clean the tire, your friend's tire, wipe it clean, no water, again start the experiment and put a hose on top, etc. Maybe the first time, maybe, what will the experiment look like? So this is the tire. You start pouring water. First, it's in equilibrium. It's stationary, right? Then as you start pouring in water and, this top half fills, so it becomes heavy, there's some leaking, etc., it starts turning. Now, what decides whether it will turn like this or like this? So that's the question I want you to think about. We will demonstrate a way to do it. Technically, this is what's known as Lyapunov, etc., which is you cannot really recreate exactly the same initial condition when you start this wheel every time. It's sort of impossible to do it. And we'll see, once we reduce this problem further, a demonstration, that's why I have my laptop, where I will show you a simulation of this, not a simulation, but a numerical solution of what we reduce from here. But this is something that is quite an important point about nonlinear systems. The fact that everything is extremely sensitive to initial conditions, and it is near impossible to actually recreate the same initial condition with the same precision. For those of us who play with things on the computer, etc., that could be, let's say, the machine precision of the computer. So you define a variable with some value, but there's always a precision to that value, and that noise itself can be amplified. Okay, so that is what determines what happens initially. Whether I turn left or I turn right is completely dependent on initial conditions. All right, so there is a symmetry breaking which is happening, but that symmetry breaking is an initial condition dictated one. Okay, so this is an integral differential equation, right? There are derivatives on the left-hand side. There's an integral sitting out there. How do I, what's the way to deal with this? So what am I after? What am I after is essentially to see if I can reduce this problem further and write down only differential equations. if I have equations of the form x dot equal to some function of x, y, z, I'm in business, right? I can think about fixed points by setting x dot to 0. I can, I can actually solve it rather easily. This is going to be a pain to do it. All right. So in general, when you have these sort of equations, so that guy looks, it's a partial differential equation, all right, but at least it's not mixed. It looks like, with some effort, a couple of coffees, I can try to figure out what to do with this. This equation looks a bit of a problem. So when you have equations of this sort, any nice ideas on how to deal with them? I mean, this is summer course. I mean, you're not being graded or whatever. It's nice if you'll think on your feet and, how would you deal with it? Don't tell me that I will make m theta independent, take m out of the integral, integrate sine theta 0 to 2 pi and set it to 0. Short of that. Was that what you were going to suggest, Jitendra?
Convert I into an integral and take
I will assume constant. Sorry. I'm simplifying my life. I'm assuming constant because I'm looking at the problem, let's say 20 minutes after I've started the task. So on average, my moment of inertia is not changing. Sure, but I'm saying that on average over a long time, I'm just assuming my I to be constant, which is why I haven't written anything for I. That's just a simplification I'm doing. I'm permitted to do it in the long time case. And when people have looked at these experiments, think about the wheel, right? MR squared, etc. So on average, you see, on average, this is completely a driven dissipative system. So at long enough times, sorry, thank you for raising that. I forgot to mention this. Thanks, Jitendra.
Integral m r squared, then you could have taken d theta, integral d theta.
Correct. Except I'm lazier than you, so I've taken I constant already. Yeah. Otherwise, you'll still have a problem with nu omega, so it's not going to solve that part of the problem, of course. Right. Nu omega I can't get rid of. Yes, please. I'm just looking at time, not to be impolite. Yeah.
If you integrate that thing by parts, you get a dm dt term that you could perhaps equate to
capital M. But I'll still be in trouble, right? Because I'll still have a derivative sitting with the sine thetas and then an M. So it'll just go on.
Yeah, but then you can substitute.
You want to, but then I have an equation which has also has del M del T. That's a good start. Try that. Try that as an exercise. It's a good point. I mean, of course, it's an unfair question that I'm asking because I know what I want to get at, and you guys don't. But okay, that's an advantage of old age, huh?
We can take Fourier series.
Oh, very good. Yes, that's correct. Whoever asked this or answered this question. So one way to think about this problem. So this is the trick. So whenever you see trigonometric functions, so you have sine theta multiplied by m, everything is depending on theta. One trick is to look at Fourier series. All right. The reason that helps is, as you guys know, different combinations of sines and cosines, etc., the integrals, many of them vanish. All of you are familiar with Fourier series? Someone said kind of. Have you sort of encountered it at all? I mean, do you know if there's a function f of x, how do you sort of expand it in a Fourier series? Yeah. We won't do much more than that. That's fine, right? I mean, I won't be doing anything complicated because it's hard for me to do more complicated stuff. So here and there's another reason why here that helps, apart from the fact that there are sine thetas plugged in, so you can multiply things and use orthogonality, etc., of the bases and, help yourself. The other thing, of course, it's a periodic problem. Right? So you can expand things in the basis of sine and cosines. Quick question, and this is this is a question of intuition. Which of these functions? So okay, forget which because we just need to worry about Q and M. Are both of these functions odd, even, not clear, mixed? By that, I mean, if I change theta to minus theta, it's not, I mean, I'm not asking a deep mathematical question. Huh? Just picture the wheel, because we'll use that to, get rid of a few terms. Do you think that q theta minus theta, etc., or m theta m minus theta, does it matter? If it did, I wouldn't ask the question. Okay, that's a good assessment. No, but are you sure that's true for both q and m? Just think about m and q. Q, I agree, because if it's if I go this way, that's why it doesn't matter. What about m? Is that strictly true for the mass distribution? Think about it. Think about it while I just write down, ouch, the Fourier expansion, because you were saying that you may not have been all that familiar with, right? So I will write, let's say I don't mess up so that's my series. Okay, so I'm going to write my mass as a Fourier series, and I'm going to write Q those ANs, BNs, QNs are what's known as amplitudes. This is right. Great. So now you guys substitute things while I take a break and tell me what the answer is. I don't want all the answers. There are many answers, but let's go to where we want to go. And I'll give you a clue. First, start with the equation for I omega dot, because the minute you try to, plug this in, you will find certain nice cancellations, so you will know what you want to do with the other equation. Okay. Can erase this, right? You don't have to do that. You can think about your talk. Just do the first equation for me, and that's enough. All you need to do, you get the picture, right? All you need to do is put this guy in instead of m. It multiplies with sine theta, the expansion there, and then there's an integral. That's all, right? Keep in mind that these amplitudes are no longer theta dependent, right? So the amplitudes come out, well, yeah, they're still inside the sum because they're labeled with n's. The reason I'm doing this was because you might see equations of this sort, in other things that you do. Right. And the others are all zero because you're multiplying with sine theta, etc. Very good. So what's the equation at the end of the day? So you have I omega dot plus GR with a pi, right? Because of the integral. Because there's a factor of half which comes down, integral 0 to pi, blah, blah. Very good. So this means that the other values of n, so if I'm trying to come up with a closed system of equation, you remember the sort of thing I gave you as my wish list to have something like x dot equal to blah. So here I already have a nice equation which has just one dot as in time derivative, I omega dot equal to blah, right? And you know, on a good day, one can solve this equation, right? Or not, because this, we do not yet know what A1 is, right? It's not a constant, okay? So what you now know is, because on the force balance equation just picks out A1 and none of the others are there, so even if the higher ends contribute in that mass conservation equation to form a closed system, you can just look at the lower harmonic, the lower coefficient, which is going to be just the B1s, what is it? Q1s, B1s, which appear there. Everyone with me? So you can again plug this in. Now you're going to take time derivatives here, so there'll be A dots, etc. And once you do this, I will write down the final form. So can I erase this? And then you will get, so the general equation will be this. Right? A dots and B dots. Now I will only couple it with the A1s here to form a closed set of equations. No higher A2s, B2s, nothing will enter the game. And so I can end up with this coupled equation. So I'll write it in a form which looks sort of familiar to some of you, certainly some of the students of ICTS. Okay. So my rather complicated problem of the chaotic water wheel has now reduced to a set of 3 simple differential equations which you can solve not by hand, but which you can solve in general using any simple piece of, calculator. Okay. The question is, if I solve this, do I get omega versus t? Because we saw the water wheel, one would hope that the solution of this, at least in some range, and we'll see what that some range is, will essentially give you an omega versus t, let's say this is 0, 0, will give you something which, the sign changes, the speed of rotation changes, etc. I mean, the experimental data will be much nicer than what I've tried to draw. But whether a solution of this in some parameter range, because you have to make sure that your kappa is not so large that you're always leaking things out, and so you don't move at all. Or the other limit, you have to ensure that the water flow is not so weird that, things are overdamped. Right? But you should hopefully, when you solve this set of differential equation, and you guys can go home and do it, you will hopefully get an omega versus t, which is just as chaotic and just as devious. All right. So at least to some of you in this room, and I'm sort of looking here and there, this set of equation reminds you of a very fundamental set of equations in the history of chaos in how this field developed a few decades ago. This is really, and I'll write it in that form because that will help me to just make a few additional points on the chaotic water wheel. This is essentially what's known as the Lorentz system. And the Lorentz system, I mean, you're the one aerospace, right? No, some of you were aerospace. So maybe you guys have seen it in some context in your coursework there. In the Lorentz model, of course, this idea came in from ideas of convection, right? And Lorentz's paper is very beautiful to read. So please do read that paper. It's not hard to read. And he worried about the convection problem. And I'll write this equation in a slightly different way, and you will see why, the sort of why it might in hindsight seem obvious that the convection problem reduced to the Lorentz problem, as does this. Okay, so let's look at this equation and then try to understand just a little bit more about where this equation is. Now, so for those of you who are kind of pesky, in a good way, of course, you might say that, couldn't we get a solution here where omega is 0, where there is no rotation? In other words, what I'm asking is, what could be... That's not me. That's someone who's online who's not on mute. Or yeah, that's probably true. Or it's trying to tell me to shut up and let you guys work out what the fixed points are for this set of equations. So by fixed points, when is A dot, B dot, and omega dot all three equal to 0? That's one fixed point, presumably, but there are two others certainly that I'm looking for. Go ahead. I mean, it's a simple calculation, right? Just set the left-hand side to be 0 in all these three equations, find out what the set of fixed points are. As you'll see something nice, and those of you who've done a little bit in convection turbulence, you'll find something which starts to smell like what's it called? The Rayleigh number in a convection problem. That's really for the ones who've done a lot of fluid mech, like I suppose knows the Rayleigh number. Not sure you guys know what the Rayleigh number, you know? So one is fairly obvious, right? It's clear that you'll get an omega equal to 0 solution, right? When the wheel doesn't move at all. And you can convince yourself how that can physically happen. So one you will get is the following. Is one fixed point will be 0, q by k, and 0. You can just substitute in, in case I made a mistake, just substitute and get it. No, because I put 0 here, I put 0 here. That calculation shows that that fixed point is right. And then there is another fixed point, which is the rotation case. And this is the interesting one. Is where, you assume that kappa is not equal to 0. So here you make a you make the substitution. Sorry, this is with distracting. That's okay. And so there are two fixed points. I mean, those are the fixed points when they're not in the chaotic regime. And we'll see, a little bit about how you can bifurcate from there. But then you have a rotation case where the strength of rotation is given by that formula. That's again from the fixed points. All right. The way you get it, in case you're quizzical, is again set everything here to be 0. And now you substitute omega back in there. So you'll get in terms of omega squared. Right? And okay. So the point is the following. This condition is exactly satisfied when, and then if I take this downstairs, when this number is greater than 1. And that number is what you might think in terms of a Rayleigh number of the flow. That's when the onset of rotation happens. So the idea is the following. So you begin, let's say, with a fixed point, which is 0, no rotation. You start pouring water. You can go to a steady state fixed point, which satisfies certain criterion. And then you would get a rotation, which is given by omega. However, when you solve this, there will be regimes in the parameter space when this omega versus time will start to resemble a little bit of what I've drawn. So let's try and understand when that parameter space happens. So to get there, let us now dive into and show you exactly what the most sort of canonical example, and I'll try to finish this in the next 15 minutes so that and take a break and go back to Navier-Stokes. And now that you have some idea that chaotic solutions can emerge from simple considerations, we can go back to Navier-Stokes. But let's look at the Lorentz model. It's full glory. Any of you know how to plug my computer and put the screen on? I'll figure. I don't need it right away, but I need it at some point. Oh, I need to connect to the Zoom also, right? For screen sharing, and you can give me the Zoom thing. Can you just email me the link, Ritik, so that the email is there by the time you log in. Okay. So you guys remember the set of equations. So they are of this form. Have to be careful here. Y minus x. So you see, this is very similar to the form we derive for the chaotic water wheel together. This is known as the Lorentz model. It's one of the sort of most sort of foundational canonical models to look at chaos. So before we analyze this a little bit, and that will depend on how much time I want to go spend, let's look at solutions of this. But before that, a few quick points. Firstly, is everyone, oh great, thanks. I was about to do it in a few minutes. Is everyone sort of familiar with the notation, right? So I'm in a three-dimensional space, X, Y, Z. And then I have these real parameters, sigma, R, and B. And I think if you've done other courses in fluid mech, then you might sort of think about sigma as the Prandtl number, R and B as some other numbers, etc. But what's important is you see that this is also a dissipative system. By that I mean, if you calculate the total energy from this XYZ, you will see that there is a decrease in energy. And you see that because there are these, for example, X dot has a minus sigma X with it, right? And sigma is positive. So of course, there'll be an element of dissipation there. So just the writing of the Lorentz model. The model is visible, right? Okay. No, I'll write it here. Okay. It's my terrible handwriting. I'm not sure it matters what's visible or what isn't. Okay, great. So what we are going to do is we are going to have a look at what solutions of this equation look like. Then we break for tea, and then we decide whether we want to analyze this a little bit. I'll take a straw poll amongst the TAs, whether we want to analyze, because we have one lecture left, or whether we want to go more towards turbulence. Okay, but let's look at this equation and its solutions. I'll connect. Yeah, I'll now connect. Okay. And what it means to be chaotic. Sorry. Yeah, Ritik send me the link, thanks. I won't join, right? No, dear. Just turn off the light at whatever.
Excuse me, sir.
Yes.
So the lecture that we missed, that's not going to be organized.
We can do an online one, but if you guys have email addresses of all of you, you can just take a poll and just let me know. Evening, I can do it on Zoom from home or whatever. We don't need the full year. Okay. That's like Macbeth. So I should do share screen. Okay. So all that we are doing is the following. So we are solving the Lorentz sort of equation, which is right behind it. And now I will sit here so that I can make some plots. And then, so the code I'm not writing real time. I have written to test that it actually works. Let me run it. So all I'm doing is I'm solving the equation that we wrote in very simple ways. Huh? Just give me a second. And what I'll succeed in doing is it's XYZ, so it's a three-dimensional phase. So there's, three coordinates. I'm going to plot the result. I've done it up to some time 4,400, whatever. I'm going to plot the result of how the, XYZ at t equal to 0, XYZ at t equal to T1, T2, etc., how the trajectory looks like. All right, I was trying to avoid the word trajectory. Exactly, that's what it'll look like. But that's what it really is, huh? And we'll see what's going on. I've chosen my parameters sigma, R, and B with care, which means look it up on Wikipedia, so as I forget what is the range when it becomes chaotic. Where did it go? That wasn't the best start, but we will see. I think some other figure was open on MATLAB. So this is what's happening in time, huh? Z, X, Y. So you see, as time evolves, it seems, can we switch off the slide? Sorry. Where, there? Yeah. Okay, great. It's still the sort of, the solution is still going on. You see, it seems to be trapped here, which is what I think you were trying to show, right? So I started, I think, somewhere here. Then as time evolved, the solution did this, and then it seems to be stuck here. But let's see what happens if we wait long enough. Sorry, I'm just hoping what happens is what I expect and hope to happen. Now it's sort of getting a little further and further away from this little hole, and we'll find out what that little hole is. It's going further and further away, and it leaves that nest. But then it goes and it again comes back. Okay, just watch this and then I'll comment on it. Oh, the colors are nicer on my computer. You guys can see, right? I mean, it's not difficult to solve, huh? So in case any of you have access to some GNU plot, etc., you can solve it on your own. Play with it. Sorry. Still going on. Good question. I mean, you could write a Fortran or something on Ubuntu, sort of install a compiler, whoever asked this question. I mean, Ubuntu would be a sort of Linux operating system, right? So you would like to do, I mean, nowadays, at least my students use Python and stuff, which I've never used. Huh? Yeah, that's also a freely available thing. Yeah. Okay, we've had enough of this going around. I just want to show you the final outcome, right? So actually good, I can sit. So let's look at the final figure, which I'll try to plot in bigger. Yeah. Huh? Not really. For this sort of simulation, yes. Otherwise, no. I strongly disagree. I shouldn't be the one saying it using MATLAB even as I speak. There's an Android. Why did I waste my morning if there was an Android app? I didn't know. Well, that's useful. I mean, if you guys want to, because I'll show you something funny which happened with the Lawrence thing. But if there's an easy way for you guys to visualize it, which I was not aware of, then that's great. Okay. So sorry, I have this thing on my. So you see, this is what we were looking at, right? We started here. Then we went around in circles. And if you waited long enough, the solution would keep getting stuck either here or here. I'll just turn this around a little if I can do that. So for the turning thing has disappeared. Earlier, there was this nice way in which you could rotate it. Okay, but that's fine. So I'll let you go in a couple of minutes. So what I'll do now is to change my initial conditions. I started here, remember? I will just change this very mildly. And I'm going to plot. So you've seen the movie, so we can forget seeing the movie if that's okay with you guys. We'll look at the final plot just to see what it looks like, to see what's common, what isn't. So let me go here.
Coming back to the movie.
Yes.
I'm sorry, I'm seeing this question for the first time, so I'm just confirming.
No, sure.
These cycles.
Yeah.
If I translate it to what is happening at the V, does it mean that it will like do this one anti-clockwise rotation and then one clockwise rotation?
So how it actually goes, the final picture of the trajectory, if you've looked at it long enough, will have this sort of butterfly-looking wings, right?
I mean, basically the butterfly wings are like anti-clockwise motion and clockwise.
Oh no, there's no way to think about that. Yeah. So we'll come to how one should think about it. But what we are saying is that the trajectory will be going back and forth between these two. You see, they were concentrated in two areas, right? When it would jump from one to the other.
Please tell it, like, so my background is in physics. Okay?
Sure. No, that's fine. So this is, I'm plotting X, Y, Z. So the point as a function of time. So the point in the phase space, if you like, in X, Y, Z, it's going around, right? But it seems to concentrate somehow either here or here.
What does it, like, what are those points?
We'll come to that. So those would be the attractors of the system, but we'll come there. Okay, for the moment, let's keep an intuition that it's sort of either going around here or it's going around here.
I want to understand. I'm sorry.
No, what's the question? What is this here, right? Yeah, so that's an attractor. We'll come to that. We'll come to that. Huh? First, let's get the mental image, right? So yeah, we'll come to that. These two things, that's the crucial bit. You're absolutely right. We'll come to that. Okay, so oh no. I am an idiot. I should have saved the data first. Sorry for doing it in real time, but okay. I'm just making them slightly bigger. Difference between the initial conditions only on one coordinate. I'm making it differ by 0.2, so it's visible. Huh? You can make it even smaller. That's no problem. So this we saw, something like that we saw. The Zoom thing is obstructing. So you see, they started nearly at the same position. The initial conditions were really more or less the same, which is why you can't see the blue, because the red one is shielding it, right? So, and then they're going together, but very soon, you see, they tend to separate. The blues and the reds come out very clearly. The only similarity is that if I plotted them separately, they would look very similar, right? Both of them would have what you were asking. Both of them would have these trajectories which with these wing-like shapes. So the individual trajectories have diverged, and that's what's known as the Lyapunov exponent, sensitivity to initial condition, etc. So if I just change my initial condition, remember the chaotic water wheel? I told you in which direction it starts moving. You cannot, you cannot possibly recreate it. Same here. I've changed the initial conditions by just an epsilon amount. Then the system evolves in very different ways. Now, if it was all different, then what's the point of studying it, right? Because you will have 1 trillion such initial conditions, so you need 1 trillion such solutions in physics. That's no good. What is common is the fact that even if the individual trajectories are different, so one may have gone like this, then come here and done this, and then spiraled out. If you waited long enough, the dynamics start to look very similar, right? So the analysis and the interpretation of these things that you were asking should be independent of initial conditions. What is dominated by initial conditions, and that's what's known as, the fact that it has a positive Lyapunov exponent, is that the trajectories are diverging out in time. So what we'll do is we'll take a 5-minute break. We'll come back and probably strictly another 5 or 10 minutes on this system. Then we close shop and we go back to Navier-Stokes. I was hoping I'd sort of finish this before the break, so that it's the end of a chapter and I can begin the new section of the lecture. But let's take a break first, and then we come back, so that if there's some questions on this, let's address this. Then look at the ddt of x dot squared plus y dot squared plus z dot squared. Hey, how do I get rid of this? You all know? Okay. That's it. Now I got it. So this is what I was discussing with some of you. So if I change the R sigma B parameter so that it moves away from the chaotic thing, you get a trajectory which is not going to look like what the chaotic trajectory was. So play with this. I mean, this is a way I just wanted to introduce you guys this equation. Play with this equation. It's a lot of fun. Sorry? Do you mind just showing the code? Showing the code? Yeah, of course. Sorry, where did the Zoom go? I mean, the code is simple. I mean, there's not much to show, right? It's just a Fortran thing where the main thing is this, where I'm just integrating the code. Right? So let me show you how you can do it rather than the code itself, because that won't help you so much. So we can try. So you can, who asked me the question? Sorry, you, right? So you can take initially x, y, and z to be whatever value you want. 1, 1, 1. Doesn't matter. you choose these values, what is sigma, R, and B. So there's a range when this becomes chaotic for B equal, I don't know if you remember, but some 1/3, whatever. Yeah. And there are range when it's not chaotic. It's like Reynolds number in flow. I mean, Rama has told you all. So now the derivative, you sort of, there are various ways in which you can integrate an equation numerically. So the simplest would be to take x dot as the trivial thing would be x t plus dt, choose some t. Beginning with some initial condition at t equal to 0, where you had your values. This I can solve by hand. Let's say dt is 0.01. So x at 0.01 minus 1, because I've taken x0 to be 1, divided by 0.01 is equal to that number. Let's say sigma I've taken to be 10. This is 10. Okay, 1 minus 1 is 0, so I have a problem. So let's take 2. 1, right? And so you have your value of x at 0.01 to be whatever that value is, right? Huh?
And then you just plot the values of the
That's right. And then you go for y and z. But you will find that if you solve these equations just by this, that's not a very good approximation. There are better approximations numerically to integrate an equation. But essentially, all numerical integrations are trying to do is to get you from some values at t to the next step. That's all. There's nothing very deep about this. Okay. So, where are we? Of course, the Lorentz problem has some nice symmetries, which is the xy going to minus x minus y, etc. And you'll find this symmetric. So the question you can ask, and this has to do with the issue of dissipation, and probably I should, yeah. So someone sort of, starts screaming at me in about 10 minutes or so. Should I stop on chaos and Lorentz, because that's not what you guys signed up for. Okay, so, all right. The thing to worry about, you saw that how these trajectories were evolving, right? So imagine these were my two initial conditions in the regime where I chose the value of b such that the answer solutions will be chaotic. The way they were evolving was the following. Then they separated exponentially, then each did its own stuff, but they look very similar. Now, if you sort of, go ahead and actually stare at these trajectories for a very, 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 very long time, which I haven't, then what you will notice is that these trajectories tend to, they started, someone mentioned the word phase space. I think you did, right? So they started in phase space trying to explore a lot of that space, right? By phase space, I just mean X, Y, Z. And then they slowly seem to settle on a volume, let's say, which was much smaller than that cubic box that I had drawn, right? So they were going around maybe like this. So if you just follow my hand, so there's sort of all the trajectories are kind of nearby and sort of going around literally in circles around something, which we will call the string attractor, right? Maybe we want to strictly.
This is also in V and E, so V is also varying, right?
I mean, that comes from the x dot, y dot, z dot. We didn't plot the V, of course, but yeah, I mean, it's a dynamical system. So
keep changing for this place, where they will sometimes go fast.
Right. I mean, you saw that, right? When it was stuck, it was going a bit slowly, right? Because, it's a complicated set of equations, so a priori. But I'm just talking about the x, y, z, okay, and the volume. But you're right. I mean, in phase space, you want to look at xv, and for sure, it will speed up and stuff. So the idea is the following. The idea is, okay, how many of you all are familiar with the notion of phase space? because if many of you aren't, then we can actually sort of bury this ghost right away and move to turbulence. What was my question? No, that I remember. How many of you are familiar or not familiar? What was it? How many of you are familiar? Okay, so you're familiar with it, I hope. Yeah. Okay, so the point is the following. So just trivially, for the couple of people who weren't, so the phase space is like the state of the system, all right? So if you think about some simple sort of Newtonian mechanics, you typically associate with a particle its coordinates, right? Position, velocity, and that forms your phase space, all right? So if your system, let's say, has the freedom to explore coordinates and velocities between some minimum and maximum, all right? As it evolves, is that range unchanged or does that range shrink? Let me put it in the following way. Is that clear? I mean, I'm talking to, I think, the 2 or 3 people who were not very familiar. Is that clear? So you want me to go a little slowly? Okay. Suppose this is my, suppose this is a piece of chalk. So it can occupy, let's say, coordinates between here and here. And let's say it has velocities, which I cannot show like this, but let's say it has velocities between 0 and 5. All right. So now, as this chalk is being tossed around, let's say it can always go from here to here and explore values between 0 and 5. So the phase space is on one axis is my coordinate. Let's say x. Here I have y, the velocity, and this was the initial volume or the initial range of values that it could access. And as time evolves, it is always, moving around this point, right? At every time, it has some x and some v. Now, it can happen that this area can start diminishing. When do you think that can happen?
The dancing thing will come into play here.
Yeah. So, for example, if there's friction, the velocity or the speed can slowly become, the particle can go slower. So you may not be able to reach velocities, let's say, which are here. And so this area starts to move, starts to shrink, okay? So phase space is the space constructed from the coordinates that the particle can access. So in this sort of dynamical system, we'll try to quickly see one aspect of it, which allows us to define what a trajectory, what an attractor or a fixed point is, and then we can slowly move out. So what we are, so now going back to where we began with, there were these trajectories. The trajectories started like this, and then they slowly were circling around the same area, right? So with this notion, it seems kind of, expected that the phase space is probably shrinking, right? It doesn't have the freedom it had to explore more coordinates in that x. I didn't show v, but in that x space. So is there a general way in which one can understand this? That's the question that we're going to. And then what does that mean for the chaotic system? So let's write it in more general terms. I'm writing this set of equations symbolically as x dot equal to some function of x. All right, where that capital X could be a system which has small x, small y, small z. All right, so far so good, all of you? Good. So now let's construct some surface S of t on which the trajectory is moving. This is some closed surface which has some surface area S of t and volume V of t. I'm going to move in that, right? So remember this rectangle I had drawn. So that was this. It was 2D, but in 3D, surface is one dimension lower than the volume. So I'm going to move here. So question is, the volume of this guy in time, does it come down or does it stay the same? All right, that's a kind of easy question. So if I go from time t to t plus dt, let's say, then this surface, let's say, has changed like this, right? Now I measured and I found the trajectory like this. After t plus dt, I found the phase space surface to be like this. Those are the coordinates that I sampled. So what we want to ask is, what is the change in the volume of this guy? So essentially, the volume of this guy, just trying to see if there's some easier way I can do it. You all have done, this sort of some algebra related to how you manipulate volume. Okay, so let me just make the statement, and then maybe after the class, those of you who want to go through this detail, we discuss, and that would be great. So what you end up having is the volume of this will just be the divergence of the function into the volume. Okay. So let's accept that on faith. Let me not go through this derivation. What you have to do is, for those of you who want to look at it, so what you do is look at the change in volume, Vt plus dt minus Vt. That will be the force into the normal of this surface, and that's the change. And then you apply, I forget the divergence theorem, which sort of converts the integral to the divergence, and then you get this. And this is a standard way you look at this in Goldstein or any classical mechanics textbook, right? So it turns out that if the right-hand side has a divergence which is negative, right? So V dot equal to some negative some minus C into V, that would mean that the phase space volume will shrink exponentially, right? So you can go back and calculate the divergence of the right-hand side of this equation. I assume that you're smiling because it's very trivial to do, and so you will do it, right? It is, it's not difficult, And you will find that the divergence of this is going to be strictly negative, which is why you found those trajectories hanging around what are known as the strange attractors. Very good. So you can actually, look at these fixed points of this system. So the Lorentz equation is a very beautiful model to play with. So go back and worry about it, and then, figure out a little bit more about what is a strange attractor. The funny thing is that unlike fixed points of a one-dimensional map, or, a lot of systems which could be a point, a line, a surface, for these chaps, and that's awfully hard to calculate often, these attractors, these sort of structures around which these trajectories go around forever, those typically tend to have dimensions which are not integer dimensions. Those dimensions are non-integer dimensions. Explain what? The non-integer. Now, okay, let me just pause okay, let me give you the following example of a non-integer dimension. No. Let's begin with, he's smiling because we had this discussion about his slides for tomorrow, right? So actually, Ritik might be the best person to explain this because he's worried about it. But I'll give you a simple explanation. That's a one-dimensional line. That's a straight line. Who said no? Okay, that's the best we can do. That's a one-dimensional line. Now suppose I split it into three halves. Some of you know what's the game I'm playing, right? It's called what's known as a Cantor set. And then I take this piece off. Okay. in the remaining thing, I play the same game again. All right? And I keep on playing this game again. Okay, for the remaining half an hour or so that I'll switch to turbulent, one of you can continue playing this game on the side. Sorry? It was in the question, okay, I don't remember. Okay. But then you all solved it, no? Okay. And so if I continue playing this game, 1/3, 1/3, 1/3, etc. Eventually, I will see from a slight distance, I will see a bunch of points. Now, I'm going to ask you whether those points are one-dimensional. Do they make a one-dimensional thing? Or is in whatever way I can calculate dimension, which is box counting, Hausdorff, it doesn't matter. Or is it going to end up with a dimension which is not one, which is not an integer number? It turns out that in the Cantor set, it's the most sort of, famous example. The dimension is.
It can't be like make out that unit of one. They're going for grade, like.
No.
That's what I'm understanding.
No, then is the point. No, but I'm going to look at I was given the full set, right? So I'm going to understand the dimension of these points. So dimensions has a sharp definition, right, in geometry. So I'm going to ask myself that given these are my endpoints, how do I define the bunch of dots, which is what you're after, what you're saying, the fact that they're all sort of spread out in this way, once I iterate this process, then how do I calculate the dimension of this? Okay, and that's a sort of completely different here, which let's not get into right now. But that's a lot of fun working on these dimensions. I mean, there's some, you can play with these, right? I mean, you can get, the Koch curve, right? So you can begin with something like this, which has a finite perimeter and a finite area. There's someone from mathematics here, you, right? So he will tell us that you can eventually end up creating these structures. And then again, and you keep on breaking them. And then you end up in the sequence as you go along the sequence, you probably end up with something which has what, an infinite perimeter which cannot be kind of defined in a conventional way, etc. So there are lots of these fun things that you can do when you start, fooling around with reality. And this is sort of the ideas which came in the second half of the 20th century, starting with Mandelbrot's work, etc., which were revolutionary in changing our notions, especially of nonlinear systems. Before that, we were all used to, happy integer dimensions, etc., as a way of thinking about things. Okay, enough fun and games. So now let's get into things that I have been wishing to inflict on you guys for some time. Okay, very good. Back to Navier-Stokes. I'll just park to experimental results, and then I will start going into some opaque worlds, but stop me, we will do it slowly. It doesn't matter. I don't have to finish what I wanted to finish. That's good for all of us, probably. And we will. So I will just park the experimental results here, which is what we will try to see how much of that we can get from mathematically from the equations. Which two do I want to give? Stop me and tell me to remind you guys what this is, if you've forgotten. You remember both these? Take velocity differences between 2 points separated by length L. Take the square of it. Take an average. And you'll find that it grows as L to the power 2/3. Unlike what you would get for smooth functions where it would have grown as L squared, right? If your things were arbitrarily differentiable, then the velocity difference would be just gradient into the separation and the gradient would be a constant, blah, blah, blah. Okay, so let's try to see what we can get from this. So, who cares about? Okay, so I won't do Kolmogorov because I've got bored of doing it. So let's look at the following. So consider the following function. Ritik, it's not visible, right? Because now I would like it to be visible. I'll explain what I'm writing in a sec. Huh? Such that. Okay, so kernel semantics, don't worry, it's a function. It's a function of R vector, which is centered at R equal to 0. You'll see why that becomes useful. So the function could be, let's say, a Gaussian or my hat. I mean, I don't have one, but let's say if I was wearing a hat. So that's the function. This is R equal to 0. I place the hat here. So that's the function. The hat satisfies certainly the constraint that it goes to 0 as R goes to infinity, unless you're wearing, hugely long hats, but they still have to. And that it's always greater than 0. The surface, the hat is sitting on the surface. Integral is 1, which is something that I do not know how to satisfy for a hat. So I have this function, all right? And we'll see what we can do with this function and the Navier-Stokes to try and understand these two experimental laws. Again, because we have little time, so the textbooks you can go and read up from the Kolmogorov phenomenology, which is not very hard to follow, and you can read up exactly about how to show the results that I'm going to show you in a slightly different way. I mean, in a slightly more formal way, which probably makes sense. So now, what I'm after is the following. I have the velocity field which comes from the Navier-Stokes equation, right? All right. So I would like to look at the fluctuations delta V in order to calculate this on this velocity field. So one possibility could be I take this hat and I apply it on this velocity field and then see what happens. But when I apply this hat doesn't have a sense of scale, right? There is nothing L coming out of the way I have defined it. I've defined a function which is at R equal to 0, which decays nicely as R goes to infinity. I can add other properties. The R-GR integral will be 0. The mod R squared GR integral will be finite. RGR will be 0 because of symmetry, right? Because it's entered as a positive, minus, etc. will cancel. But the sense of scale doesn't appear. So I can do something more. I can massage this function. You're still with me, right? I mean, stop me the minute you all are trapped. I mean, at least, be with me in some sort of, coarse grain sense, which is what we are going to do also. I can then define a surrogate function G labeled with L such that for those of you who've seen things like scaling functions, etc., I've sort of scaled things with L. So I've given a length scale in the problem in defining this function itself. So if I'm going to now apply this hat on my velocity field, it comes with the idea that there's a length scale L that I've set in the problem, right? Because everything is falling off with respect to L. So now let's go back and, define a new velocity field. So a coarse grain velocity field such that, sorry, this is, I might ignore vector signs in a, that's because I will be running out of symbols. So this is the coarse grain. So this bar is just because my V and U look very similar. So that would be even more of a disaster if I try to play that game. I need omega because I need vorticity. So I'm running out of things. So I'll put a dash on top, which will just be so what is this? So with the proviso, of course, that I'll explain all this in a minute. So what I've defined is, just look at it physically. So I have the velocity field at a point X, at a sharp point X. I have now integrated that field around between X and X plus R, local, Siddhartha, and I've applied this hat on top of it, and I've defined a sort of average velocity over a scale L. Okay, with me, guys? I mean, stop me, because the rest will be a lot of algebra, but if you get the spirit of what I'm about to do, and the algebra, I'll just sort of give some statements of some inequalities, etc. The rest is easily done. So I've defined a coarse grain velocity field. Now, this is not as crazy as you think it is. I mean, it's probably crazy, but it isn't as crazy because you are, in a physical measurement, let's say in a wind tunnel, in a wherever, you are never measuring things at a point, right? You are always measuring things around a point, right? So things are never measured, take a probe or something, push it in. You're actually measuring the velocity, at the scale of which the probe is. So this is what it's doing essentially. All right. So it is measuring. You had a question? You don't look happy, no? Okay. So you are essentially measuring the velocity on a scale L at point X. In other words, for some of you, for example, who may have done, especially our friends from engineering who've done fluid courses, this in some sense is a large scale filtering. You are actually filtering the velocity field up to a cutoff, from large up to a cutoff scale N. Any fluctuations below that you're ignoring, right? With this sort of kernel. Okay. So you can then look at the converse problem, which is what's the high pass filter? The low pass is this. The high pass, what's the symbol I've used? Very creatively, I've used this. So that's a bar, that's a prime. which will be nothing but the full signal minus this. Okay. So now you can you can go ahead and actually do it. You see, I can write this equation, v of x, because it's centered at x and this is a function of r, I can take this inside the integral and nothing will change. Right? Why? Because I'm going to use this condition. Again, I'm deliberately slowing down. I mean, stop me, at least let's all of us try to understand the construction as much as we can. And we are still at the construction stage, at the conceptual stage. After that, if things go downhill, we'll apply the brakes at some points and get to the results. Maybe this is, I might sort of switch gears and go to a simpler model. But is this construction still okay with you guys? Sure, all of you? If any of you have a doubt, just feel free to voice it, huh? So, I hear the doubts being voiced only when I turn towards the blackboard, so I don't know whose voices they are. Okay, so this is a function of x. G is a function of r. All right. So I can write v of x is equal to v of this thing with vx plugged in, and it makes no difference. With me? Why it makes no difference is because I have chosen a function whose integral is 1.
I'm actually lost.
You're lost. Okay. Okay. V of x.
Actually, I'm lost from the start.
You're lost from the start.
But I'm blaming myself it's down here, so it's okay.
Okay.
Continue with the
I'll continue. Okay. Fine. Maybe at some point you'll catch up. Okay. Maybe it was a bad idea to do it more formally. I was probably thinking of you guys.
What is v of x plus r doing?
Good question. So the answer to that question is the following. So the guys can see me, right? Whoever is the online person. So let's say the bottom of this bottle is my function, which I said I was just joking on being like a hat, which is true. You can think about it as a hat. Now this hat has a certain length scale L. All right. And this hat is, imagine it's a Gaussian. It's exponential minus r squared over L. All right. Okay. Now I'm going to multiply that. This is just a matter of definition. I have an underlying velocity field at some point x. I'm going to multiply that velocity field with this hat and integrate. Now, when I'm going to integrate it, I need to integrate. So I'm centered at x, but I need my velocity field everywhere within that hat. So that's why you have that vx plus r. That's why g is a function of r. Is our friend happier? Okay. All right. So this is how you do, for example, coarse graining hydrodynamics, let's say from molecular dynamics or whatever, from some microscopic theory. Yeah. So I have a velocity field which I've defined as v of x everywhere. Let's try a different way. Okay. So in this region, I want to have an idea of what my average velocity is. So to do that, I construct a function g of r, which could well be just equal to 1 within here and 0 outside. It's going to satisfy that. I probably have to divide by a normalization factor, but it's going to satisfy that. Huh? So within this region, which is centered at x, so at every point, Vx plus r, Vx plus r, Vx plus r is a variable here. Remember, I'm going to integrate over r within this box. I'm going to calculate the function multiplied by the velocity field. And I'm going to get some sort of an average velocity within this box. Okay, does that make sense at that level? And I'm going to average it in some sense. He's already looking at the watch. And I'm going to average it in some sense because I've additionally said that this function has a length scale L. Where is the length scale? Think about the Gaussian problem. I would have, let's say I've taken G to be exponential minus R squared over L squared. That's where that length is coming. Now I take the velocity field. I just make sure that that person, so I take that velocity field, I multiply with this Gaussian filter around X, and I'm going to get a average velocity over a length scale L. That's all I'm doing. Okay, does that make some sense? Huh?
Are we taking the function as only g of r or whatever d part dr is?
Oh, that's the integral. D part dr is not the function. That's just integrating. Yeah, in d dimensions. So that's just integral dd. Okay, wait. It could be dr vector if you like, huh? But that's just the integral. Okay. Fine?
Yes, yes.
At least the so basic idea is fine. Yeah. Yeah. All right. So guys, I mean, it's not. It's just that I didn't want to teach Kolmogorov phenomenology for another n+1 at time in my life, so where n is a large number. So I wanted to do it in a different way. All right. So with that in mind, I can write v of x. Let me write it. Okay. V of x, I'll do it slowly, huh? Is equal to v of x into 1. Right? I know 1, there are many ways to write 1. One of the ways to write 1 is this. All right? Now, this is a function of r. So whether v of x stays outside the integral or inside the integral, it doesn't matter. Okay, so I can stick this inside. Then I can make the subtraction. All right, and then I end up, with whatever, I mean, I don't care about this, huh? Where delta V is the difference of velocities between points x plus r and x. So you slowly see that I'm trying to set up a formal machinery to which I can answer the that 2/3 question. Okay. I'm going to skip a few steps now, I think, in the interest of not being pelted with. So I'll just. So with this, so we are fine with this kernel. So I'm just reason I was going through my notes was I was trying to see if I can come to the final, well, not the final, but the working equation without torturing. So now all I'm going to do is multiply this equation with G, integrate it, and then I end up with the following equation. Some force. So this equation, after this sort of, well, this procedure in physics would be something you can call co-squaring or whatever. After this procedure, you see there's only 1 point of difference between the Navier-Stokes equation that you had and the one that we have with this sort of, with where this length scale is involved. And it is in that term. It's some sort of divergence of a tensor, stress tensor. What it shows you physically, we'll end here and we'll come back and pick it up from here if any of you all are still coming back on Thursday after this, is we will see that because I have done a sort of filtering at large length scales, this term is actually what shows you what you've learned phenomenology in the first class, and also I think implicit in some Rama's lectures, I'm not sure, is the fact that the large scales are now going to drive my flow. And the interesting question happens is what happens if I take this L becoming smaller and smaller? I would expect this term to vanish. The equation slowly starts to resemble again my Navier-Stokes. But at an arbitrary length scale L, if I cosine, I get this additional term, which shows what is the kind of driving that, how is the large scales driving the flow. What we really want to go from here is to actually go ahead and then, in the next class, if you all are there, and then actually try to sort of show these two results, which comes out. The algebra won't get any more complicated beyond this idea. I will just introduce a couple of definitions. Don't be very worried about it. Those are definitions which we will use to actually prove those results in the next session. That's the other question. Yeah, it's a bit like the Reynolds stress. That's exactly what I've done. So tomorrow we will do it. It'll be even more stressing, the Reynolds stress part of it. So what we will do is you take a slight deviation from the truth, and we will compute some norms of. Norms are just, take integrals of the function, raise it to some power, and then so I'll define those terms for you guys. But we'll start from here and we'll try to show the two fundamental results in turbulence. Sorry? Yes. There's one?
So you will take it on Zoom or somewhere, someday, right?
Yeah, I mean, we don't need to, but yeah.
I think they all want to just come back.
Yeah. We can do it on Saturday, right?
No, Saturday I can. So on Friday, I'm actually leaving for a meeting, but I'm back the next week. I mean, I'm going to Israel on Friday. So if I get the visa in time. Tomorrow, I have 2 comprehensive exams. Sorry, guys. Tomorrow, I'm really, this week, and then on Friday, I also have 2 comprehensive exams. But the week after next, those of you all are still interested, at least then we can do a wrap-up class on some of the nicer problems in this area without doing maths. We can do it online, or those of you in Bangalore. You all have my email ID, and all of you have each other. So just send each other an email and tag it, and we'll do it online. Huh? So, I have to take an exam in the next semester.
That's what the mail said.
Oh.
Certificate, you need to have 90% attendance plus an exam. That's what the mail said.
On the last class.
Oh, not the last.
So this exam thing, I'll ask the office, I'll take your email IDs. I mean, maybe, what I was about to prove, I could give that as an assignment in the next session.
I'm doing Bengaluru on 7.
On Thursday, you're not here.
I'm Thursday here. 6th time here.
Friday.
7th is
Friday.
Yeah, I'm also leaving on Thursday night, actually, if I can get my visa on time. So then, or Friday, when we have to leave? Friday, both of us are free. So, okay, so next Thursday, exam. So I'll take the normal class, and after that, just we will have a quiz, and that will be fun. I'll check with Rama. Yes, sir.
It will be last class, so can we have a group photograph together with
Yes.
This guy has some plans.
No, I think there is a plan for that anyway. So there will be a group photograph on Thursday because Veena was asking me today. So I said, check when Rama is available. I'm available on both these classes, whereas Rama should be there with us. That will happen on Thursday. So we'll try to, finish this a bit. So I will give you so these are these sort of calculations. So the functional analysis is Kolmogorov's textbook on functional analysis, and the derivations, etc., are from old lecture notes and also papers by Peter Constantine and Greg Ink. I'll give those references on tomorrow. I mean, the next class. Okay. Yeah, I've been a bit sloppy with the references, but maybe if you're still there, maybe this derivation you can kind of ignore, but Uriel's chapters on phenomenology is very good, and that's something that you can read up in Uriel's textbook.